which derivative gives max min and nothing else other than increasing, decreasing, and so on and so forth. But which one gives max min? First. Thank you. So please, the reason why I'm saying I put that in is because right here, when we had this table, no, maybe on the second one, on the second table, yes. So it's better to look at this. So please understand, when you look at the second derivative, you cannot say anything about max min. There is something that I need to prepare you for, but the second derivative, without knowing anything else, where are my notes? My notebook. Okay. So if we don't know anything about this, and I only have the second derivative, I cannot say where the max min is. Yes, you can say, but I can tell. Yes, you can. So this is something very important. I'm going to write it down, but I want to explain it for a moment here. When the function, assuming it's continuous, of course, if the function opens up and then it changes concavity here, it must have a maximum. Most probably, right? It must have a maximum here. So that is what is called the second derivative test. But there are other conditions. So this is not carved in stone. But when I see something like this, I may look and see if the function has a critical number there. If it has a critical number, then it will have a max. If it does not have a critical number in this territory, then it will not have a max. Like, look here. It's opening down, it changes concavity, but it has no max. Okay? The horizontal asymptote is not considered a max. Okay? So I have to give you the exact point of the maximum. If I can't, and I can't, then there is no max there. Now, but if the first derivative has or the function has a critical number there, then this must have a max in this territory. The same concept here. If the function opens up and there is a critical number between these points, it will have a minimum. And look what happened here with this graph. Yes, it did. We found a critical number, or it was given to us. We had a critical number here. That's why, because the second derivative tells us that the function opens up and there is a critical number there, this must be a local minimum. And moving on for this last part. So the function opens down. It should have a maximum in between 8 and infinity, but it does not because there is no critical number there. Same thing here. This should have a maximum here between negative infinity to no, because there is no critical number there. Here, opens up. It has a minimum. Yes, because there is a critical number there. Okay, so very important to understand this concept. Okay, so which derivative gives inflection points? So I don't want you to confuse these two, ever. So what will we answer here?
Second.
Yes, I just need more blank sheets. Okay, yes, this is the second derivative. How many hypotheses does MVT have?
2.
2, indeed. Only continuity and differentiability. How many types of symmetry are there?
2.
3. And how many are applicable to functions?
2.
Exactly. How many steps are there in graphing a function? The correct answer is this. No, I'm kidding. Many. So we jotted down like 16. Well, if we were to be 100% correct, it would probably be more than 16. Okay, but we jotted down 16. So many steps, very important steps. Okay, now the floor is open for your questions. Anything you want, anything you need help with, anything you want to suggest. If not, we'll continue with graphing. We'll have, of course, more examples. Does anyone need help with anything?
Can we look at the discussion from yesterday, please?
Yes. Yes. Here it is. What was the question? Hello? Anyone?
Sorry, the wrong one pulled up. I'm trying.
It's right here.
Yeah, okay. Well, I'm trying to look at mine as well. I'm sorry.
Oh,
Excuse me.
okay. So this was in the notes from last night. We went over the discussion last night.
Okay, I understand.
No, but you may still have a question. Well, what was the question? And the table is right here. So it has two absolute max at 2 and 5. This one is also relative, but this one is not. And it has an absolute min at 0, -2. Anything else?
I had the numbers 2 and 4, but I didn't have their like y coordinates included, and so I didn't get.
Well, when if it's a specific question about the grade, I cannot talk in front of everyone else, though. I'm not allowed to do that. So if you want to stay after class, we can discuss that. Is that okay?
Yes, of course.
Perfect. So if you have a minute after class, we can discuss it. So anyone else, anyone needs help with anything, or we move on and look at another example of graphing. One example is not enough. Okay, then, so I'll share my screen so we can choose another problem. Where is my button here? Okay, got it. I found it. Okay. So we looked at, I don't remember, one of these. Oh, I do remember. We looked at, I chose something that was symmetric because I also wanted to discuss that in detail. So I think it was 47. Yeah. So maybe we should look at a different type of problem, like, for example, something with a radical or something with a natural log. The ones with trig, they are extensive. The steps and finding solutions and solving trig equations.
Yes, please.
Okay, well, which one? You choose. I chose last time, you choose this time.
58 looks good.
Okay, so we want to look at 58. Okay, that will be most probably much easier than this. Okay, so 58 it is. So S of x equals x minus sine x, and they're telling us two complete rotations between 0 and 4 pi. Okay, perfect. So remember what we did last time? It took me, I don't know, 20 minutes or more. This time we're going to go much faster through those steps. I'm hoping that everything will be even clearer now. Okay, so I know that in this particular case, I don't have to analyze domain because I am specifically given 0 to 4 pi. I only have to start my table immediately. And if it gets crowded, then I will have to like I did last time when it got too crowded, the numbers were too close. If I can't see, I'll go landscape. Okay. So this is a difficult situation a little bit. So first of all, remember we start discussing S of X. No derivatives just yet. So what I need to determine here is, first of all, the x-intercept. So again, we skip domain because it's already given to us. So the x-intercept is when S of X is 0. So x minus sine x equals 0. We don't know how to solve this. So I have to try, and there is no feature in the calculator for this. So what I have to try is go to y equals, because I still have to find the x and y intercepts. They're mandatory if they exist. Okay. So I will put x equals sine x. So x is one function, sine x is the other function, and I will choose the viewing window exactly what they gave me. They gave me 0 to 4 pi. No, that's not what I meant. So I meant, first of all, I'm irradiant. That's good. Okay, so I want 0 to 4 pi. So I'm not suggesting that you should graph the function before graphing it by hand. But I have no other way of determining the solutions just yet. We do. It's Newton's method, but we haven't discussed Newton's method yet. So I'm going to make the scale as pi. And the highest that I can have here is, so sine cannot be more than 1 or -1. But I have this x, which can be 4 pi. So 4 times 3 is 12, plus or minus 1. So somewhere between, so 4 pi, can it go under? No. So it cannot go under. But I'm just going to have -2 and positive 15 with a scale of 5. So I will see the graph, but I need to determine the x-intercepts. Okay. So because I already put this in, I'm just going to go back and change it and just put the function in because I need to see the whole thing. I mean, it's the same thing, but it's better to just have the function in there because I chose the viewing window, the whole thing. So, okay. So we have x minus sine x. And now when I click on graph, I can click directly on second and calc to determine the x-intercepts, but I have to see the graph. I have no choice. So here's the graph between 0 and pi and 4 pi. Okay. So obviously what we see here is that it has potentially x-intercepts in here. So I don't think it's going under. Can it go under? No, because 0 minus, yeah, it can go under, actually. It can. So I'm going to have to zoom in here or just simply determine, obviously, there is only one x-intercept. Maybe at 0 is also, right? One of them is 0. But it goes under. There is no other way. So I go to, and it would be difficult to determine the other solution because obviously one solution is 0 for sure. 0 minus sine 0 is 0 indeed. But I want to find a second solution right here. So we go with second and calc. And I want to find the 0. You can use the x-intercept if you put a second function as y equals 0. But right now we're going to just say 0. So I want 0 to be the left bound. And I want the right bound to just make sure that I go beyond the intersect. Okay, so let's see. It may not give it to me. It may jump to 0, back to 0. We'll see in a moment. Okay, so no, I don't want to guess. No sign change. So it means that it has just a 0. That's it. So is it possible for x minus, so let me see again. According to the graph, I'm going to zoom in a little bit. So zoom in. It doesn't appear, but I'm not super certain, so I need to investigate a little bit more. So one more time, second in calc, I want the 0. And I can also use the table. So I'm going to use the table in a minute if I'm not convinced here. So I'm going to put 0.1, the left bound. And I want to go beyond this point and see if it gives us anything. It did not take my left bound, or I didn't click. So I don't want 0. I want a little bit to the right. So that's my left bound. And I want the right bound here. If it says again that it doesn't change, okay, so obviously there is no sign change. Okay. So at 0, okay, 0.00001. Okay, 0.01. Okay, 0.1. Okay. Okay, 0.5. Okay, so it's going up. So it's going up, so there is no sign change. Okay, fine. I have to convince myself that it's increasing, and apparently it's increasing. Okay, got it. So then the only x-intercept is here. So only when x is 0. Perfect. Now we have to so x and y intercepts are the same, right? So s of x equals 0, or when x equals 0, we get the same point. So this function crosses at the origin and nothing else. Fine. So now we have to find this value at 4 pi. So in y equals, I'm sharing my screen again. So in y equals, basically I have to plug in 4 pi to see what's happening here. So where it's going at the other end. Okay, so at the other end, they say it's 0.5. I have to, that's not what I meant, sorry. 4 pi. Where is my 4 pi? 4 pi. Okay, as expected, 12.6. So 12.6. As we said, 4 times 3 is roughly that. Minus sign, which is 0 anyway. Okay. So there is nothing else about the function from the function itself. In this case, that's all I needed, x and y intercepts, and to determine the values at the endpoints. Okay, now I have to continue with the first derivative. So let's see how